Hi, welcome to my channel Talent Talk. I'm Dr. Tom Anderson, Senior Tutor at the Department of Chemistry at the University of Sheffield. My talk's going to be called Journey to the Centre of the Atom, in which we investigate the atomic structure that we think we know. A little bit about my institution, the University of Sheffield. So, this is a picture of the Department of Chemistry where I work at the University of Sheffield. This is where it's located, if you weren't already aware of that, good transport links. And here's some pictures of the city. It's got a good location, a lot of things happening in the city, and very nice for the rural Peak District nearby as well. We're a World Top 100 university, and 99% of our research is great, paraphrasing. And that's everything I want to say about the University of Sheffield for now. But if you want to ask me about it in the tutorial, that's fine. But I want to now focus on the subject of the talk. So I'm going to start with a very open-ended question. What is science and what isn't? Because people often get the wrong idea about science in what they picture. If I've asked you about my discipline, chemistry, for example, what a lot of people will picture is some flasks full of colourful liquid like this, maybe even smoking and fuming in the background of a Hollywood science lab. There is actually a reason why we sometimes do that, by the way. It's not just to look cool, but they'll think of things like that. They may think of a very stereotyped scientist who looks like Alfred Einstein in his white coat, holding something up and saying something like, "Eureka, I've found the answer." But that's not what science is about. Science is not about finding the answers in the back of the book. In many ways, it's more about finding a more interesting question. There is no such thing as a true proven scientific theory, and there is no such thing as scientific truth, although that term is often bandied about. All there is a more refined theory compared to the last one we have. We can disprove our old theories, but we can never prove them, and that is the basis of scientific investigation. And it's with that in mind that we now look at the history of where our conception of the atom came from. To do this, we first must go all the way back to ancient Greece, and specifically to this gentleman here, Democritus of Thrace, known as the laughing philosopher. You can see him laughing there. And he came up purely with a philosophical idea, it was at the time, this notion of atoms. His idea was, if you take a piece of cheese and you cut it in half and you keep on cutting it again and again and again, can you continue cutting it in half forever, or will you at some point reach the smallest possible particle of cheese that can no longer be subdivided further? So a slightly more everyday example today might be Lego, for example. So if we take James May's Lego house here and we try to break it down, we might be able to break it down into walls of Lego like this, but sooner or later we would reach the smallest possible particle of Lego. We can't break the Lego brick in half. That is an atom, if you like, in this analogy of Lego. And the word atom or atomon in Greek means indivisible or uncuttable. That a prefix means not or un in Greek. So the idea was the atom was the smallest possible particle, can't be subdivided any further. But although this idea was bandied about at the time, it was not a popular idea, because Aristotle, the grand old man of ancient Greek philosophy, didn't like the idea of atoms, because if you've got atoms, there must be gaps in between the atoms, which are by definition vacuums, and Aristotle did not believe that vacuums exist. Not that sort. So because of this, the idea of atoms never really caught on at the time. But the ancient Greeks had a lot of different philosophical ideas. Someone who you will have heard of is Pythagoras of triangle fame. But one of the other things he did, he was obsessed with the idea of trying to interpret the world in terms of kind of a mystical version of maths, using maths to understand the world. And one of the things he and his disciples looked at was the idea that there is maths behind music, which there is. So, for example, if you take let's say a guitar string here, and you strum the whole string, you might get a note C. If you put your finger in the middle, we say you put a node in the middle, and it's now only vibrating half the length of the string, then it is a note C up one octave. And as you can see on this diagram here, it follows a predictable pattern. As you put more nodes in, the note goes up in frequency. And so all fair and good, but what Pythagoras thought was this must reflect rules in nature in general. So one of the ideas he and his disciples came up with was what they called the music of the spheres. The idea that the orbits of the planets and the distance between them, they thought they were on spheres at the time, hence the name, they thought that this must be related to that musical relationship I was just talking about. So there was this idea that the world ran on music theory. Now, why am I telling you about this? You'll understand when we come to the tutorial. But that's a bit about ancient Greeks. Greece rather. Now, over 2,000 years later, it's easy for us to look back and think of all this stuff as, oh, they knew nothing, the ancient Greeks. They only had 4 elements. You've probably heard of these: earth, air, fire, and water. You look at the periodic table nowadays, like that one behind me, see there's hundreds of the silly things. Why would you only think there's 4 elements? Well, first of all, it's not just an ancient idea from the past. It still underwrites our Western society today, because it's not just about earth, air, fire, and water. These were related to the 4 humours of the body, as it was thought. For example, blood corresponds to air, phlegm to water, and so on. And this, as I say, this influenced Western medicine, the idea that you bled people to try and balance the humours, which didn't work. But one of the things it influenced was this idea that when you're eating a meal, you need to balance the humours. So you start out with the savoury things and you finish with the sweet things. And we still do that today in the Western world. That is not a universal human rule. You do not get starter, main course and sweet dessert in other cultures necessarily. And it all relates back to this idea of the 4 humours and the 4 elements. So don't be so quick to look down on the ancient Greeks, especially when what they said by elements was not what we mean nowadays by elements. The meaning of words can change. Instead of saying something had the nature of earth, what they meant was it's a solid lump of stuff that sits there and doesn't take on the shape of its container. Does that sound familiar? Instead of saying earth, air, fire and water, we could just as easily say solid, gas, liquid, and if we want to be really charitable, plasma for fire. The meaning of words can change, and what the Greeks meant by these terms, elementa, was really more like what we call phase state nowadays. So be careful not to judge ancient civilizations that way. But let's move on to where our modern conception of elements comes from. And that is in the scientific revolution of the 17th century, when science became, the idea of hypothesis testing really became clear, and the idea that you could purify things down to find the purest possible substance, and it could no longer be subdivided beyond that. So this is a list of elements from then. We've changed the symbols since then, and we've got more accurate masses. You can see one of those on there, lime, is now known to be a compound, so they haven't quite got it right yet. They haven't been able to separate the 2 components. But these are pure substances, so these are elements. That was the intention. So a list of elements is a list of all the unique kinds of stuff in the world. But where did that idea come from? Well, one of the big things that changed then is we were able to measure things much more quantitatively, not just saying, oh, it's like this. We could measure things in perfect ratios. Antoine Lavoisier was a very rich French scientist. He was so rich he was able to prove that diamonds are made of carbon by burning them with a giant magnifying glass, as you can see here. Combine them with oxygen in the air, which was not obvious. Finding oxygen was a whole other story in itself. We combine carbon with oxygen to make carbon dioxide. But we now know it's not just some carbon and some oxygen. We were able to measure it precisely, and people like John Dalton realized this, and with these precise ratios came to the conclusion that for every 1 lot of carbon, you've always got 2 oxygens together to make 1:2 ratio. C plus O2 makes CO2. And from this, if you've got to the idea that it's always in a precise ratio, that implies that it breaks down to it breaks down to as small as possible pure part of that substance in order to make that ratio make sense. So Dalton revived the idea of atoms. It's worth noting that it's not that everyone believed him at the time. The idea of atoms was very controversial into the 20th century. A lot of people even said, oh yeah, it's just a mathematical shorthand, I don't really believe in atoms. We're so used to thinking everyone accepts atoms, it took a long time to get acceptance. And the periodic table is a more rational way of arranging the elements, where, explaining their different properties and how they relate to each other. Mendeleev wasn't actually the only person or the first person who did it, but he was the best self-publicist, so we remember him. So here's our periodic table of elements. But how does that explain it? Why is hydrogen at one end? Why is radon at the other end? Well, we've got these over 100 different types of atoms, which is another way of saying what elements are. And we can combine them in an almost infinite number of ways to make new compounds. So we're not just limited to that 100 types of pure stuff. We can make different compounds which have all sorts of different properties. Most of the molecules in your body are based mainly just on carbon, with a few other things. So that just illustrates how much possibility there is there. But this doesn't answer the question, just what is an atom? It's kind of a mathematical abstraction so far. What is the actual structure, appearance of an atom? Well, atomic theories let us rationalize these ratios in chemical compounds, as I said. So methane, for example, CH4, all single bonds, as we now think of it. Carbon dioxide, double bonds, carbon and oxygen. Hydrogen cyanide, nasty stuff, a triple bond between carbon and nitrogen. But notice, in all these cases, carbon always has 4 bonds, and that is a general rule. So that tells you something about the internal structure of carbon. Why does it have that property? And those are the numbers for those bonds. Well, no sooner had most people started to accept the idea of atoms, Marie Curie, Henri Becquerel and other people came along and showed actually atoms aren't indivisible, so the whole name atom is not correct. So they found that, among other things, for example, radioactive uranium would fall apart and release 2 new elements and some high energy particles called electrons. So we knew that electrons must be part of the components of the atom. It's not just a round billiard ball as it was on those pictures I just showed you. There is stuff on the inside. Okay, so what is this stuff and how is it arranged? Well, again, we're used to this picture of the atom that we're used to, and we don't really think about the fact it wasn't obvious at the time. People had to come up with theories. So Gilbert Lewis, who is someone you'll find out about in the context of acids theories, because his acid theories were better founded than his atomic theories, certainly. He had this idea that a lot of elements have 8 electrons in the outer shell, and you can have electrons or you can have gaps, and you can put electrons into gaps to make bonds in like carbon dioxide and so on. So he came up with this idea that, what has 8 points on it? A cube. What if an atom is cube shaped with an electron at each point, and you can have atoms that have all of the electrons filled up or with gaps in, and you can put them together to make bonds. Great idea, completely wrong. And the reason why we knew it was completely wrong was not just, oh, everyone knows atoms are not cubes. No, nobody knew it back then. But we knew that you could put points together to make a single bond, share 2 electrons. You could put the sides together to make a double bond, share 4 electrons. But how do you put 3 corners of a cube together to make a triple bond? You can't. You can make a quadruple bond, but they rarely exist in real life, and certainly not with carbon. So that was a dead-end theory, which you never hear about. You act, in textbooks, they act as though, oh, science theories, it just goes, nice, clean, smooth passage. That's not how it works in real life. There are lots of dead ends. The more common mainstream theory of the atom at the time was the plum pudding model, which I think was thought up by some Victorians when they were feeling hungry. This idea, they knew electrons had a negative charge and the atom as a whole was neutral. So this idea that the atom is a big blob of positive charge with little electrons in there as the negative charge in there. Like the plums in a plum pudding or currants or whatever. But it's not just enough to come up with a theory nowadays, we have to test it. We're not like the Greeks. So Ernest Rutherford tested this, or rather his PhD students did, they did all the actual work, and he tested this by, they fired some particles through the atoms and they found that what they expected to do was they were just spread out by that big blob of positive charge. What actually happened is they bounced back in the middle, which should be impossible. It showed all the mass of the atom must be concentrated in the middle, very concentrated, what they called the nucleus. There's a great quote about this. He said, it's the most incredible thing that ever happened to him. It's as though you fired a 15-inch shell from a gun, like in the bottom left. You can see how big that yellow 15-inch shell is, at a piece of tissue paper, and it had come back and hit you. The atom was so much more concentrated in mass than anybody had expected. And this led to this model, which you will have seen before, the Rutherford-Bohr atom from 1913. There's Niels Bohr, who was one of the people behind it, as you can imagine from the name. And what is this model made up of? Well, we've got positively charged protons in the nucleus. There, the number of protons defines what atom element the atom is. So hydrogen has 1, helium has 2, and so on. That's what tells you what the element is. You can't add another proton without changing the element. And then around it, you've got these electrons, which are negatively charged, equal and opposite charge to the protons, but they're very small, very, very low mass, almost massless. So the mass of the atom is not contributed to significantly by the electrons. It's the protons. And the third component, neutrons, which are neutral, uncharged particles in the nucleus, and you can add and remove those without changing the element. It just changes the mass, and we call those different isotopes, which you may have heard of. But those are still, you can have different kinds of oxygen or whatever, they just have different mass in the nucleus. Okay, so that's the Rutherford-Bohr model, which you'll have seen before in school. And is this the end of the story? Have I finished a couple of minutes early? Well, this atomic model is immediately recognizable symbol. It's used a lot to represent science. You'll have seen it all over the place like this. And there's just one small problem with this. It's wrong. That model is not correct, and we've known it's not been correct for over 100 years. So why does it still appear in textbooks? Well, we'll begin to discover that as we do the tutorial. First of all, let's see, you might want to pause the video at this point so you can read it. See if you can spot some of the problems with this model, which you may not have thought about before. A cluster of positive protons in the nucleus and electrons orbiting on those nice, neat circular orbits outside it. Positively charged protons, negatively charged neutrons. Do you see a problem here? Pause the video and see what you think. But I'm going to move on. Then there's the octet rule, which I touched on before with Lewis and his cubes. This idea that you'll have heard it before. Atoms, they have 8 electrons in the outer shell. Great, except apart from that one. Hydrogen and helium, they only have 2 electrons in the outer shell. Okay, that's a bit of a problem, but and that one as well. So there's a whole row of elements, what we call the first row of the transition metals. They have more than 8 electrons in the outer shell. This octet rule is not a very good rule, is it? It only works for a few elements. They're just the ones we care about a lot, like carbon. Okay, so these rules that people memorize are not useful. They do not explain what is going on, and they actually have lots of exceptions to them. So if we really want to understand what's happening with the electrons, they're not moving in nice, neat circular orbits. They're doing something quite different. We will have to develop a better atomic theory. How are these electrons actually arranged around the nucleus? How can some of these shells hold more electrons than others? How does that nucleus hold together? How do chemical bonds form, sharing electrons? And most importantly, perhaps, is it possible to draw any of this? That's what we're going to be looking at in the tutorial. And a hint as to where some of this comes from, think about what I said before about the music of the spheres. The ancient Greeks weren't wrong about everything. So that in conclusion, in the tutorial, we're going to discuss these gaps in understanding. We'll deduce what's wrong with this atomic model, which we all learned in school, and learn maybe a deeper level of what chemistry and physics tells us about the structure of the atom that makes up us and everything in the world we live in. Thank you very much, and I hope to see you in the tutorial.